Richard Taylor, who will be talking us through how to keep your API keys safe. So over to you, Richard. Thank you.
Okay, thanks very much. Thank you. So I'm the CTO and the co-founder of a company called Critical Blue, and we kind of specialize in mobile app security, and in particular, we kind of work in the area of securing communication between a mobile app and a mobile API. So I'm going to share with you kind of some learnings we've had from customers about things that can go wrong with API keys and things. So the reason you should care about this is that if you don't care about securing your backend your backend web API or securing your API keys, then they can be abused, and this can be something that can damage your business and maybe even the proposition of the app itself. So what I'm going to do in this talk is I'm going to cover some kind of real-life type examples using a synthetic example, but basically we've generated an example that we've developed in Kotlin, and all the source code for that is going to be made available at the end, and then give you a link on GitHub. The backend is developed in Node.js, and basically it's pretty standard. It uses JSON over HTTPS. So in order to illustrate the points, I'm going to show you kind of 3 different attack and defense kind of scenarios where initially the API key is not particularly secured, and how that is attacked, and then go through some kind of more extensive types of obfuscation and the types of attacks you can have against those. So in terms of why is this a problem? So this is kind of a good example is Pokemon Go. It doesn't really need much introduction. Obviously, it was a very successful app. Summer last year, more than 650 million downloads. And basically, it's a sort of online, it's an app with a back-end API. There's a map on the back-end API, which is communicated via this private API. So the API itself is hosted in Google. The API format isn't published. And it was abused when the Pokemon Go app first came out. So what happened was, there was obviously a massive uptake and therefore quite a lot of load on the back end, probably more than was expected. So when the app first came out, there was a mapping feature inside the app that basically allowed you to see Pokemon characters in the surrounding area, and that particular feature actually caused quite a lot of additional load. So what happened is that Niantic, the developer of this app, decided to remove that feature quite soon after release in order to kind of reduce this back-end API load issue. But there was a bit of a kind of backlash from the community because people like this feature. And so what happened is this initial version of the app didn't actually contain that much in the way of security in terms of locking down the API access or making it difficult to reverse engineer the API. So people in the community reverse engineered the API. GitHub projects sprang up with Python code that allowed you to make API calls. And indeed, loads of online maps appeared that basically showed you the entire map of where all the Pokemon characters were. And this was really an abuse of the API, because obviously this affects the gameplay and also increases the back-end load again, and wasn't really what was intended. So Niantic hit back. They increased the level of security inside the app. They added pinning. I'm going to talk about that later. They rejected execution on rooted devices. They added various checksums inside the API request to make it more difficult to work out how to generate a valid API request. So really, I mean, I suppose the learning from this is that you need to be aware of this issue. And there's no such thing as a private web API, in the sense that if you have an API that your app talks to, you are publishing the app, and therefore all the mechanism that's required in order to be able to access the API must be inside your app, and therefore is in the public domain, and it can be abused. And this is an ongoing concern. This happens frequently. This is a kind of news report from the beginning of the year, which is done by a company called Fallible. You basically have a static analysis tool where they basically took the entire app store, downloaded the APKs, and trawled the APKs for keys. Now, this isn't just API keys. This is all sorts of credentials that have been left inside apps. So this is a real problem. You need to worry about all sorts of credentials you might be leaving behind in your app. But I'm particularly going to talk about means to access the API because if that's discovered, then there are attacks against your API that you potentially need to worry about. So in order to kind of talk about this, we've developed this app called Ship Fast, which is basically a courier app. This is a slightly contrived example, but this is actually an app we've developed. All the source code is available. And basically, obviously, it uses a back-end API, and we're going to illustrate some of the issues you have with this. It's a courier app where basically this is the app that the individual drivers would use, and it tells them where they can pick up packages, basically where to pick them up from, where to drop them off from. So the assumption with this app is that the drivers are being paid by ShipFast, and this is the app they use to work out where to go next. So in order to illustrate this, I am going to show you an embedded video of this running in an emulator. So you can understand how it works, and then we'll talk a bit more about how the code works and how the API works. Obviously, you need to log in. We're using auth0 here, so we're logging in with social login in this case. We get an OAuth token. So that's obviously used to identify individual drivers. Once you go in, you basically get a map of where you are, located based on your current location, and there's information about your current shipment. Initially, there is no current shipment, but you get information about the shipment, what the shipment is, a gratuity that might be associated with the shipment, which I'm going to talk about later, where you're going to pick it up from, where you're going to deliver to, etc., and its current status, whether it's been collected by someone or not. So in order to say I want to be able to pick up a shipment, you basically have to click the I'm available button in this app. And as soon as that happens, you basically get to see the nearest shipment. So obviously the ShipFast want the nearest driver to go and pick up the shipment to make it as fast as possible. So you see where it's from and where it's going to. So you can see here that this is where it's pick up from, Office Means Suppliers. And this is where it's going to let go land. And the status is ready, so it's basically ready to be to be picked up. So you basically say, yes, I accept this shipment, which means that you don't have to go and collect it. So you drive to the pickup point. So when you reach the pickup point, you obviously say you've collected it. Drive to the destination, probably on a road rather than this blue line, and then you drop it off when you say it's delivered. Okay, so that's the shipment. It's now complete, and you can go back, and then the driver can look for the next shipment. Okay, so you notice that also there is a gratuity associated with this as well. So in this particular model, to illustrate the point we want to make, there's also an additional gratuity. So in addition to the wage you're getting for being the driver, there is an additional gratuity which is paid to the driver associated with a particular package. But the idea is that ShipFast only want to show the nearest package because they want to minimize the time before the pickup. So looking at this from a kind of transaction kind of perspective, this is what's going on between the app and the back-end API. So we've got this kind of initial login process where you go to an authorization server, something that's given an OAuth token. That's the first login process. Then using the OAuth token, you get your active delivery, which initially is going to be just a 404 because there's no active delivery. So this is a communication from the ShipFast app to the back end. Then you can use the API to get you the nearest shipment, and that basically takes your authorization OAuth token and a latitude and longitude, which is going to come from your GPS coordinates. And notice how it's structured so that the endpoint kind of follows the model where you basically just want to see the nearest shipment. So that returns you information about nearest shipment, and then if you accept it, you go through the process of updating the state to accepted, and then you're picking it up, and then you're delivering, and then you're done, and you've delivered the shipment. So in addition to the OAuth token, there is also an API key. I haven't shown it yet, but that's what I'm going to talk about. So as well as identifying the individual user, you also want to identify the piece of software. So this is a common practice that is a particular piece of software will have an API key associated with it that's used also in the authorization. So basically, you would only accept an API request if it both had valid OAuth token and also a valid API key. And this is a kind of very common model. If you sign up for a third-party API, you'll go to some sign-up page, and then it will give you an API key, and that identifies your piece of software. Now, of course, there are risks with that API key being abused because, for instance, in some services, there's a rate limit. So there's a certain number of API calls that can be made per hour or per day or whatever. And therefore, if somebody else uses that API key and makes an excessive number of calls, then that could DDoS the app because your app using the same API key would not be able to get through. So really, when you sign up for an API key, generally it says, well, don't reveal this API key to anyone. And in a server-to-server kind of communication context, that's easier to achieve. When you want to make a call from an app, then you have to have at least one API key to start, and that's a more difficult process. How do you actually secure that, given that by definition your app has to be public? You have to push your app into the App Store. It has to be able to access it. So this illustrates in our app, and as I said, all the source code is available, how the API calls are being made. This is developed in Kotlin. So you load the user credentials, which basically is the OAuth token. You load the API key, which is also used. You generate in this case, this is nearest shipment, so this generates the endpoint, generate a bearer token with the user credentials, and then basically go through the process of building up the request with an authorization header, the API key, and latitude and longitude, which is, find the nearest shipment from here, and then you go build your HTTP request, etc. So, what can happen if the API key falls into the wrong hands? So, in our example, the idea here is that what happens if somebody takes the API key? What they can do is they can build a website, which basically undermines the initial business model, which is basically to only show the shipment to the closest person. So basically, this is a website that any individual driver could go to, and basically it gives them an advantage over other drivers because it gives them a complete picture of what's going on, and they can pick up other shipments. So again, I'm going to show an embedded video to illustrate this. So on the left-hand side here, we've got complete standard app. Right-hand side, we've got this website. It's a single-page application. You can see here that the API key, for the purposes of illustration, the API key is shown here. So the API key has been extracted and is being used. There is a possibility to log in. And basically, you can then type in any kind of location that you want, and also a kind of sweep radius. So basically, the idea is that this website gives you an insight into where all the shipments are at any given point. So you log in, and actually this is going to the standard authorization server. So it's spoofing the request to the authorization server. It's going to the authorization server as if the real app would. You type in the real credentials, and then you basically get your user authorization OAuth token. So now you have an OAuth token, I have an API key, and therefore this website can spoof any request just as if it was the app. So what it does is basically show you a list of all the shipments that are available. So obviously the shipment that you would normally be shown would be the closest one, which is 1 mile away, that has £6 gratuity with it. But actually what you're going to do, of course, is you're going to go after this one because although it's further away, it's got a higher gratuity. So basically you say grab it inside the website. And that basically is making calls to the backend API and has basically grabbed that particular package. And then you can go into the app as normal. So you log into the app using your normal credentials. You say you're available, and then immediately you see you've got this package. It's already been accepted because it's been accepted by the API calls happening on this side, which allows you to obviously go and pick up that package and then deliver it. And then you obviously you've got the best gratuity here. You've kind of undermined the business model. You drove further, and also you're reducing the average gratuity that drivers not using this website are getting. And next time you're going to go after the next highest gratuity value. So that's selected the £21 one, and that's now being shown. Okay, so that sort of illustrates what the attack is. And again, all the code for this and the website is available as well to see, so you can see how it works. So what's going on here is that basically you now have two different clients that are using the same API key. So ShipRadar, you go in here, you provide your user credentials, and then basically what it's doing is taking a fake location and then doing a sweep over locations and building up a picture of all the shipments which are available, and then allowing you to accept the one that you want, which is probably the one with the highest gratuity, pushing that to the back end, and then you go into the app and then you kind of complete the normal process. So because it's a single page app, you can go in and you can see what the code is. So if you actually look at the JavaScript that's actually in this ShipRadar website, you can see basically all it's doing is very simple. You're just doing a sweep over locations. So rather than calling one location with your real location, you're basically creating some fake locations and fetching the nearest shipment and basically building up this picture. Now, obviously, there are some defenses that you can put for this type of thing. There are some defenses that you can put on the back end. Yeah, for instance, you could have a velocity for an individual user. So you could look at the locations that they're reporting and look at the implied velocity between them. And if the velocity is too high, it's not believable, then you could kind of block on those API requests. So there are definitely things you can do behaviorally on the back end as well to protect against these types of attacks. But this is just an illustration of a wide class of types of attacks. But also you have to be aware that there are classes of attacks kind of called more like a Sybil attack, where you actually have multiple different users basically subverting the system by sharing information in the way that they're not intended to. So you might actually have multiple users logging in and providing a sample of different locations and then sharing that information. There might be fake users, there might be real users. And that is much lower, it's below the radar. It's much more difficult to kind of stop that. So there is motivation to try and lock down the API to make sure that only the official client can actually make these calls, and it's being done in the way that was originally intended in terms of the API structure. So in terms of keeping secrets safe, really, well, there's two attack surfaces. There's the attack surface of it being in transit, and there's the attack surface of it basically being reverse engineered outside the app. So I'm going to talk about the in transit case first. So the thing to remember here is that the assumption here is that the mobile app talks to the back-end API. It's always encrypted. It always uses TLS. So encryption provides that end-to-end security, but it doesn't stop API keys being stolen, because essentially in this type of attack scenario, the attacker controls both the channel and the end device. So what happens is the attacker sets up a PC man-in-the-middle proxy. They create a self-signed certificate, they push it onto the proxy, and they basically push the same self-signed certificate into the device itself. So the device itself starts trusting that certificate, which means that the TLS connection is open between the app and the proxy, and it thinks it's safe. It thinks it's a trusted source, and then obviously it's decrypted at this point, and then the information then goes to the API. But the point is that any information going past here is being decrypted. So if there's any API keys, any kind of static secrets, then you can steal them at that point. And that's quite frequently if the security is not very high in an app and you have static API keys, that's usually the easiest way to actually steal them, is the kind of man in the middle. You don't even have to worry about reverse engineering the app. So the way you kind of defend against this is typically pinning. So the idea of pinning is basically what you say is, rather than trust what's in the trust store on the device, actually bind the certificate you expect to see on an API backend inside the mobile app itself. So that you put something like that, either the entire certificate or a hash of the certificate into the mobile app, and basically when the TLS transaction occurs, you expect to see that certificate and only that certificate and reject anything else. So this is great, except for two things. First thing is that it creates this dependency between your API backend and your mobile app, so that when you want to rotate the certificate on the mobile, on the API backend, you can't do that without updating the mobile app at exactly the same time. And of course, you realize that you can't actually update your mobile app at exactly the same time, because you always have some users that would take some time to update. So you're immediately into a kind of management issue of having two certificates at least that you kind of rotate with a kind of time window where two certificates are acceptable. So there's got some management issues to it. The other thing is that actually pinning is quite easy to bypass on rooted devices, but because the pinning is actually typically uses particular hooks in the HTTP stack, they are well known, and there are kind of framework modules that run on rooted devices that basically undo them. So there's still a possibility, if you're trying to protect secrets in transmission, that actually these frameworks will allow you to basically unpin again. The implementation of it is quite straightforward. In that, this is the OK HTTP client on Android. This is in Java. There's a certificate pinner class, and basically you provide a URL and a hash of the certificate you expect to see into the HTTP client, and that basically means whenever you access that particular URL, it will only open the communication if it sees that particular certificate. So in our case, how did the API key get stolen? Actually, it's a lot simpler in this particular case. This is actually just, it doesn't need to use the man-in-the-middle route, because if you look at the code in our example of how do you load the API key, well, actually all it does is it basically loads it from the manifest. So it's kind of a convenient place to put it, except of course that the manifest is trivially easy to see. So basically you just take the published app, you unzip it, you run some tools to see the original version of the manifest, and then you have basically the manifest directly in clear text. So it's providing very, very little defense. So that's really, really not good practice. So the next level up, really, how to kind of protect an API key, is that you kind of have to, in order to kind of close down the in-transit potential attack vector, and to make it more difficult, what you have to do is basically not transmit the API key. So in this kind of model, and this is used quite widely in kind of more security-conscious apps, you kind of break the API key down into sort of an actual API key, which is the identity, and also an API secret, and there's a kind of one-to-one between the identity and API key and the secret. So for every API key, there's a particular secret. And this secret kind of provides the authentication part. So the thing about the API secret is that you should never actually transmit it. So you use this kind of process called HMAC in order to avoid transmission. So what HMAC does is basically you can take some or all of the aspects of your original message. Like in this case, I'm taking the URL and the authorization token, and I'm putting them through a function, just through a string, and I'm putting that into the HMAC function. And I have the secret, which is inside the app, not inside the manifest. It's more secured inside the app. And basically, this goes through the HMAC function, and that generates a signature. And that signature is derived both from this part and also the secret. Now, so underneath this is using a cryptographic one-way hash function. And the advantage of using this kind of cryptographic one-way hash functions is that you can see lots of these signatures, but you can't basically reverse engineer what the secret might be simply by seeing lots of signatures. So it's kind of cryptographically secure in that you can transmit lots of these signatures without being able to reverse engineer the secret. So the way you actually do this is you take the initial message, you kind of create this extra signature, and then you add this additional header, SF-HMAC header, along with the API key in the message. So that's what's get transmitted is the signature, not the secret. And on the other side, you basically do the same calculation on the back end. The back end obviously also needs to know what the secret is, probably looked up from the API key. You put the same stuff through HMAC, and then basically you compare what you got on the transmission. So if it checks out, then that indicates that the app must have possession of the secret, because it would never have got the signature any other way, highly unlikely. And also that none of the parts of the message which are included in the HMAC have been tampered with in any way. So it's also a sort of second layer of integrity check as well. So in terms of what the code looks like to actually do that kind of thing, it's not actually that much code. So this is what we added basically into our client to do this. We've basically got the API key header as before, and we've got a new HMAC header with a calculate API request. We have an HMAC secret, which we put in the code, not in the manifest, in the code. And then we have a calculate API request HMAC function, which basically sets up with the right key, and then adds the parts that we want to put inside the HMAC, generates a hex string, which is the signature, which is the thing we send on the header. And obviously you have to implement the same thing on the back end, probably in a different language. In our case, it's implemented in JavaScript because we're using a Node.js back end, but similar code. So when you do this, you find, ShipRadar web app goes down for a while, but then it comes back. So clearly they've worked out what's going on. They've managed to reverse engineer it again. Again, you look inside their code. You can see they've got the API key as before, but now they've got the HMAC, and they've got a compute HMAC function. Though it looks funny because it's in JavaScript, it does exactly the same thing as the Kotlin implementation. It has the secret, and it also has the parts that you're going to add in terms of the message. So they basically reversed engineered it again. And the reason is that this is a more sophisticated attack, but it's still not necessarily that hard to reverse engineer this stuff. Basically, what you need to do is download the APK, you unzip it, and then you use something like dex to jar. And so basically that provides you with some code that looks a bit like Java. So this is from the compiled code. So obviously it doesn't contain any comments, it doesn't contain any useful simple names. And most of the names are completely obfuscated because this has been through ProGuard as well. So there is obfuscated code. But the problem with ProGuard, of course, is that on the boundaries, you can't obfuscate functions into libraries. They have to remain the same. And also, if you have code which is calculating something that is going to be associated with a header, then that header has a string, and therefore it's possible to work out where that string is used, and therefore where the code is that calculates that value. So with a bit of detective work, you can always find the piece of code that does the calculation. And what you find with our kind of example is that you reverse engineer it. You can basically see, well, you can work out what this does. It goes on after this point, but you can see what it does in terms of what strings it includes, and importantly, it also contains the secret. Because the secret, though it's compiled into dex, is easy to reverse. You can see it in a Java form by using one of these tools. The previous talk talked about NDK, using NDK to secure it as well, and that's another thing you can do. It doesn't fundamentally change it because it's still obscurity, but it makes it more difficult because there are less tools around reverse engineering pure ARM compile code, and you need a bit more expertise, but fundamentally you can use the same mechanisms to break it. Okay, so basically once you have that, you can implement your JavaScript version. And this is a big risk because there are a lot of really impressive tools actually available for reverse engineering apps in terms of seeing what's inside the code, looking at either Smiley code or turning it back into Java code. There are runtime frameworks where you can basically hook any function you want and you can see what's coming in, going out, actually modify its behavior. You can obviously take an app that's been published, you can reverse it into Java, you can add your own code to it, you can modify its behavior, you can republish it. And if you can socially engineer someone into installing that app, then obviously you have an app that does all the things the original app did in terms of probably generating API keys, but may have some kind of malware content as well. So the next level I'm going to talk about is, well, one of the issues here is that previously this was a static secret. So the next level you can go to is actually having a runtime, kind of obfuscated runtime secret. So the idea here is that this is the kind of modified code. You start with a kind of a base secret, but then you also do some runtime modification to generate something which is derived from something in the code, but needs runtime in order to do that. Now, there are many different ways of doing this. This is actually quite simple-minded, really. You can do clever things in terms of the calculations, but fundamentally, it all comes down to the fact that there has to be something inside the app that you can combine together in a deterministic way that will generate a new piece of data. Because anything you do has to be reproduced by the server, and therefore the server needs to know what the calculation is going to be. So the idea here is that you won't see the secret directly by looking at reverse engineering the code. This is calculated at runtime. However, even this is not unbreakable. So what I'm going to show here is how you would break this particular level of defense. So in this case, you go to basically using a debugger. So again, I'm going to show you an embedded video of this process. So what we see here is, again, it's Dexter-jar code. So this has been through ProGuard, but it's been reverse compiled. And we're using the same kind of ideas, that looking for boundaries of functions which aren't obfuscated, or some path to how a header is calculated in order to find the piece of code we're interested in. So we found, again, the new calculation, we found the kind of base secret, and we found all this additional code that creates the runtime secret before it goes into the secret key spec calculation. So at this time, at runtime, we'll have the secret key spec, but it's obviously not clear what this is just by looking at the code. So what we do is we take the app, we reverse it, and we add debug privileges, so we can basically debug a published app. And then we go into a debugger. And basically what we want to do is breakpoint on that particular function. So we know at the time when that function is going to be called, the input to it is going to be the runtime key spec. So that's the name of the function, secret key spec, and we know it's a constructor. We also know from looking at the code the exact constructor is, because they're numerous. It's the one that takes a byte array is the one we want, so that's the one we're going to put the breakpoint on. So we got the app running live, we log in. Nothing happens yet because the login process doesn't make these API calls. So we log in a normal way. We see the map, and then we say we're available. And then we immediately hit the breakpoint because we're making an API call. And then what we can see is that this is the input to the secret key spec. So basically that there is the new secret that's been calculated at runtime. And that basically you can then plug back into your spoofing client in order to be able to make API requests again. Now, as I say, there are various levels of obfuscation you can go to, but this is ultimately is a bit of a cat and mouse game, and you need to be a lot more sophisticated to do these types of this type of analysis. But you always need to be aware that it's always possible to reverse these things. So in terms of going beyond that, there are more techniques out there to go further. I'm going to talk about some of them. So there are, I'm talking in sort of general terms. I mean, there are products around this, but I'm talking about in general terms. There's the area of kind of white box cryptography. So what white box cryptography is a way of basically mathematically obfuscating cryptographic calculations. So for instance, if you're generating an HMAC, what you would do would be to dissolve the actual secret inside the code. So you basically end up with a specialized piece of code that obfuscates the calculation and the secret inside it in such a way that even if you single stepped through that code, the secret would never actually be in memory. You'd never obviously be able to see what the secret is. So it's incredibly secure, but the problem is that then your approach is not to steal the secret, your approach is to steal the white box, because basically if you can steal the white box, that white box code, and get it running in your own app, then you don't really need to know what the secret is. You just give it the right inputs and it will generate the right outputs for you in order to generate the request. Another approach, kind of beyond ProGuard, is commercial tools to do much better obfuscation, make it much more difficult to understand what's going on, and also include kind of runtime tamper resistance. So it makes it more difficult to make modifications or to run it under a debugger to do these kind of attacks. And these kind of protect the API kind of indirectly, in the sense it makes it more difficult to understand what's going on and to reverse engineer the API. And then there is also, I mean, in a sense, the ultimate protection is going into something like Trust Zone. So ARM processors have Trust Zone, which basically is a secure enclave in the processor that's not accessible even to root. So basically, if you even get root on a phone, you can't see what's inside Trust Zone. You can instantiate functions within it which you're allowed to instantiate, but you can't see any secrets which are inside it, nor can you see the code inside it. So it's incredibly secure, but also because it's incredibly secure, the process of actually provisioning code into Trust Zone is complex and has costs associated with it. So it's not very widely used because of this complexity. It's not easy to put into an app in a widespread way. There are other techniques as well. So this is something that we as a company work on. This is what Approved does. There are some other things in this area, and what they take, they kind of inspired by trusted platform modules, and the sort of what they say, what these do basically is to analyze the entirety of the app rather than rely on secrets. So in this particular scheme, you kind of have user authorization, and you also have this kind of sense of an app authorization service as well as a user authorization, and you basically need to have both in order to access the API. So the app authorization basically initiates the process and makes an integrity measurement of the entire app and runtime system. So it kind of starts off with a nonce value as a kind of one-time cryptographic thing to make sure it's non-replayable. So even if you steal traffic here, you can't spoof it. So they basically look at the entire environment of the app and provide a measurement, and that measurement is different because it's influenced by the nonce value. It's different every time. And if the measurement is correct, then the app can be given a short-lived token, which can then be used to access the API. So what's going on here is really, rather than embed a secret in an app, is that you make the entire app the secret. So you make a measurement of the entire app, and that becomes the secret. And obviously then, well, if you make any modification, if it's the same app, then it's clearly not an illegitimate client. So it basically proves that the entire app is making the call. Another thing to be aware of is that if you are accessing multiple APIs, then really the best practice is to not put especially third-party API keys into your app. You should really be going through a proxy or going through an API management layer and putting those kind of third-party API keys in that layer, because then it's on server side and it's much easier to defend. So that if the API key in an app is actually reversed, then that doesn't cause you to have to renegotiate with third parties. The idea is that you should use some kind of master API key or secret along the lines I've been talking about to basically unlock those secrets inside this proxy to then talk to the providers. Obviously there's a latency impact here, but this is a much better approach. It kind of minimizes the number of secrets that could be lost and abused, and means that the ones that there are the ones that you kind of control, and you can rotate if necessary. Okay, so in summary, so APIs can be abused in quite subtle ways. You need to be aware of this. User authorization is not necessarily sufficient protection. Depends on the app, and it depends on how difficult it is to onboard new users. But in some cases, the attack is actually fake onboarding, or actually it's actually a user with real credentials who's using some non-standard or illegitimate client in order to access the API. Secrets in apps can be exposed, quite trivially, unless you make some effort. And once that happens, then API calls can be spoofed. So you need to think about, well, if an arbitrary piece of software can spoof API calls against the back end, does that somehow change the customer journey, or does it somehow undermine the proposition? Is there something in the way this API is structured that's really important for that? So you need to kind of develop a security stance about what would happen if that occurs, you should apply basic obfuscation, at least in terms of API keys. And if you are at all concerned, you should at least be going to HMAC so that you're not actually transmitting any secrets in the channel to make it more difficult. Do some level of obfuscation, and beyond that, there are techniques that raise the bar further in terms of locking down the API access. So if you do have a bigger concern, you should be looking at those kind of things. So all the source code for the app that I showed the videos of is available on this GitHub link. And also all the levels, so basically the basic approach and then the additional kind of security that we put into it. Okay, so thanks very much. So any questions I can take? Yep.
How do you verify the app's integrity in runtime? How do you verify the app's integrity in runtime?
By going quite low level and looking at the process map and looking at the app package and the things that are in the memory at the time, and calculate what's going on inside it.
Can that be not compromised as well?
In theory, yes, but it would take a much more sophisticated approach. I mean, all of these things, ultimately they're on the client, and it's an unsafe environment. So ultimately it's possible, but it'd be much more difficult. Yep.
You said about the white box encryption that the key isn't actually stored in memory at